Okay, so what we're going to do today is we're going to practice in this video. What we're going to do is we're going to practice a few more problems on assigning configurations to chiral centers. And again, we're only going to focus on carbons that are sp3 hybridized. Okay, so how would we assign configurations to molecules? So let's look at a few more examples. Okay, so let's say we have a molecule where we have that. Let's say that's the molecule that we're looking at. We want to assign configuration to this molecule. Now, just to recap quickly, notice that we have one chiral center in this molecule. So that's the chiral center that we're focusing on, because this carbon here, the chiral center, is connected to a methyl group. If we look to the right, we have a carbon with two hydrogens, which is then connected to an oxygen or a hydroxyl group overall. And then to the left, we have the carbon with two hydrogens, but now it's connected to an aldehyde functional group. So we'll try to see how we assign priorities over here. And there are some nuances when you get to carbons that are double bonded. And so we'll address those issues in this video. So if we start here, again, to keep it simple, what I've done is I've put the lowest priority group, which is the hydrogen, on the dash. Okay, so remember, the first thing that we do is we basically assign priorities to all the groups that are connected to the chiral center. So in this particular case, again, since we have a hydrogen here, we can put that as the lowest priority. So that's 4. Okay. And then if you look at it beyond that, so beyond the hydrogen, what we have is the chiral center is directly connected to a carbon at the top, which is on the wedge. There is a carbon to the right, and there is a carbon to the left. So there's kind of a tie between all of these groups, because what's connected, the atom that's directly connected to the chiral center is a carbon in all 3 cases. So what we do in this particular case is we move beyond that atom. So what we do is we evaluate the next layer of atoms. So if I go on the wedge, the carbon is now connected to 3 hydrogen atoms. So that's the situation over there. Okay, so that carbon is connected to 3 hydrogen atoms. To the right, the carbon is connected to 2 hydrogen atoms and then 1 oxygen atom. Okay, 1 oxygen atom and 2 hydrogens. And to the left, the carbon is connected to 2 hydrogen atoms here and then another carbon atom. Okay, so we have 2 hydrogens, 1 oxygen, 2 hydrogens, carbon, and then we have 3 hydrogens. So we look at all of those groups overall, and what we see is on the right, we have the carbon connected to 2 hydrogens and 1 oxygen atom. The oxygen is of a higher atomic weight. It's a heavier element. So the oxygen takes priority over here among all of these carbon atoms. So we're going to put this down as priority 1. This would be priority 2. And this methyl group is priority 3. So that's how we sort out priorities among groups. And so now that we've assigned all the priorities, the next thing we have to do is kind of orient the lowest priority group away from us, which is naturally the case over here. So in going from the atom with the highest priority to the atom with the lowest priority, we are moving clockwise. So that means this chiral center is of the R configuration. So the configuration around that chiral center is R. Okay. Okay, so hopefully that's good. Let's move on to another example. We're going to tweak this same molecule slightly to get to this new structure. So in my new structure, what I'm going to do is I'm going to put that methyl group on the wedge. On the right, we have the hydroxyl group, but over here, the aldehyde group is connected to that chiral center. So this is the new molecular structure that we're looking at. And so now again, if you notice, we have a chiral center. It's that same chiral center at the top, but we got rid of this CH2 and we brought the aldehyde closer to the chiral center. So we skipped that one carbon here. So again, for this molecule, the lowest priority group is this hydrogen. So that's 4, which is on the dash. Okay. And then we have the chiral center, which is connected to a carbon, carbon, and another carbon. So they're all carbon atoms. So there's a tie between all of those groups, the 3 groups that are connected to the chiral center. So what we do is we go to the next layer of atoms. And so for the methyl group, the carbon is connected to 3 hydrogen atoms. So there are 3 hydrogen atoms. On the right, we have 2 hydrogen atoms and 1 oxygen atom. So 2 hydrogens and 1 oxygen. On the left, if you notice, this is an sp2 hybridized carbon, which is now connected to 1 hydrogen, and it's double bonded to an oxygen atom. So whenever you get to a situation like this, where you have carbons that are double bonded to an atom, the way we treat this is to consider this as 2 single bonds. So a double bond to an oxygen can be treated as a single bond to 2 oxygen atoms. And then if in a situation where we have to go beyond this, we treat that because it was a double bond between a carbon and an oxygen atom, we treat it as if this oxygen was connected to a carbon, because that's what that was. And this oxygen was also connected to another carbon atom because it was a double bond between a carbon and oxygen. So we treat it as if there are 2 oxygens connected to it. Now we don't have to go to that extent here. So I'm going to erase this. But the double bond would be treated as if it was connected to 2 oxygen atoms. So now if we do the evaluation, so we have carbon with 3 hydrogen atoms, carbon with 2 hydrogens and 1 oxygen, and we have a carbon that's connected to 2 oxygen atoms and 1 hydrogen atom. So again, based on atomic weights, when we do the priority, this would now be priority 1. This carbon is going to be priority 2, and this carbon is priority 3. So in going from the highest priority group to the 3rd priority group, not the lowest, the 3rd priority group, we move counterclockwise. So this stereocenter is going to have an S configuration. So this is how we sort through a situation where we have a double bond. And this would apply to carbon-oxygen double bonds. It would also apply to carbon-carbon double bonds if you were in a situation like that. So let's look at one final example, and hopefully this would clarify a lot of these things. So let's say we have a situation where we have a carbon with, okay, let's keep it simple. We're going to come back to that later. So we have a carbon with CH3. And then on one side, there is an aldehyde group. And on the other side, we have a carboxylic acid. Okay, so that's the new molecule that we're looking at. And so again, here, I've intentionally put the lowest priority group, the hydrogen, on a dash to keep things simple so that we can focus on one thing at a time. And so what we have here is hydrogen being the lowest priority group, that is 4. Now, one thing I want to point out here is for all of these molecules that I've been working with, the hydrogen is a lowest priority group, but that does not have to be the case. It could be a carbon containing group that's the lowest priority group. So maybe we'll look at an example like that in a bit. But we get hydrogen as 4. Now again, we have the situation where we have carbon, carbon, and carbon. So we're looking at 3 carbons connected to the chiral center. That means we have to move beyond. Okay, so this carbon is connected to 3 hydrogen atoms. This carbon is double bonded to an oxygen. So we're going to treat that as two separate oxygen atoms like we did in that example. So it's connected to two, singly bonded to two oxygen atoms and then a hydrogen atom. And over here, we have a carbon that's double bonded to an oxygen. So that should again be treated as carbon that's single bonded to two oxygen atoms. And there's another oxygen atom here. So what we're seeing here is carbon with 3 hydrogens to it, carbon with 2 oxygens and a hydrogen to it, similar to this situation here. So since it's a double bond, it would be treated as 2 single bonds. So carbon with 2 oxygens and a hydrogen atom. But on the left, we have a carbon oxygen double bond and then another oxygen. So we're going to treat this as carbon that's singly bonded to 3 oxygen atoms. So now this takes priority because there are 3 oxygen atoms, 2 here and none over there. So this would be 1, this would be 2, and this would be 3. And in going from 1 to 2 to 3, we move counterclockwise, which means this is of the S configuration. Okay, so those are some situations that you would definitely see as you're working through problems. So keep that in mind. So whenever you have double bonded carbon that's double bonded to something, so split it as if it's single bonded to 2 of those elements, and then go through the priority. Okay, let's look at a few more examples, some things that might show up. Now let's consider an example. Let's say this is one molecule that we're looking at. So we have a molecule. So we have that, this, that, and then we have let's say that's the molecule that we're working with. So kind of notice that again, there is one chiral center in the molecule. Now there could be molecules which have more than one chiral centers, but this is a molecule with one chiral center in it. And that's this carbon over here. So I would say you should, when you watch this video again, take some time, pause, and then try to make sure that you only find one chiral center here, okay? There should not be more than one chiral center in this molecule. So make sure that you're able to do that. Okay, so there's only one chiral center in this molecule. And now notice how I've chosen a molecule where the chiral center is connected to a carbon because this is a methyl group. Okay, so this is a methyl group. So the chiral center is connected to a carbon here. It's connected to a carbon here. There's a carbon here and a carbon here. So it's basically 4 carbon atoms that the chiral center is connected to. So we cannot assign priority to any of these groups right now because they are all carbon atoms. And notice how I'm going atom at a time. I'm going one atom at a time and then looking at what it's connected to. I'm not trying to look at the size of the group and then say that, oh, that is the highest priority group. Do not do that. That could be misleading in some cases, okay? So do not do that. So we have a carbon, 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 and carbon. Okay, so what we're going to do next is go to the next layer essentially. So if I look at this carbon, that's connected to 3 hydrogen atoms. If I look at this carbon, it's connected to 2 hydrogens. This is a CH2 group, 2 hydrogen atoms, and another carbon atom. Over here, the carbon is connected to 2 carbons and then a hydrogen, if you read the bond line structure. So 2 carbons, 1 hydrogen, 2 hydrogens, 1 carbon, 2 hydrogens, 1 carbon. So that means based on all of these, all that we can say is that this carbon should be the lowest priority because it's connected to 3 hydrogen atoms. And this carbon should be the highest priority because it's connected to 2 carbons and a hydrogen. So between the other 2, it was 2 hydrogens and a carbon. So this is the highest priority group. So we're still left with these 2. And at the next atoms that we looked at, or the next layer that we were looking at, carbon with 2 hydrogens and a carbon, carbon with 2 hydrogens and a carbon, we could not distinguish between these two. So we're going to move further. So when we move further, what we see is this carbon now is connected to 3 hydrogen atoms, but this carbon here, the next carbon in that chain, is connected to 2 hydrogens and a carbon atom. So now we've found a carbon where we can distinguish these two, and it turns out that this should be 2 and this should be 3. Okay, so now we've assigned priorities to all the groups, and notice how the lowest priority group is not a hydrogen. Basically assign priorities and it's a methyl group, but it can be any other group when you assign priorities. So the lowest priority group is a methyl group over here. And then the next thing we have to do is we have to orient the molecule such that the lowest priority group is pointing away from us, or at least imagine the molecule in that way. So in this particular case, if we imagine an axis that's going through here, and if we do a rotation, and I'm going to keep the basic numbering skeleton here, okay, or let me redo this. So what we are looking at here is a scenario like this: the highest priority group on our right, lowest third priority group on our left. The lowest priority group is on the wedge, and the second highest priority group on that dash. This is basically translated in terms of priorities. That's the arrangement that we have. So this is the arrangement we have in terms of priorities here. And so now if I imagine an axis through there, and if I do a 180-degree rotation on that, if I rotate around this axis by 180 degrees, what that would do is it would give me an arrangement. It would give me an arrangement like this. So we have 3 over here, 1 here, 4, which was on the wedge, should now end up on the dash, and 2, which was on the dash, should now be on the wedge. Now that I've put the lowest priority group away from me, in going from 1 to 2 to 3, this is a clockwise rotation, and so the configuration around that center is R. So it's of the R configuration now. So hopefully this gives you some tools, and now you can do this rotation. Doesn't matter how the molecule is oriented, you can do this rotation. So hopefully this gives you like some idea about how to approach a problem like this. And so what we're going to do is in the next video, we're going to start talking about molecules where there are 2 chiral centers, and then we'll start looking at diastereomers a little bit. Okay, but you should be able to apply a similar thing to molecules with more than 1 chiral centers. That should also be possible. Okay, thank you.